Okay, let's go and get started today. We've got a couple lectures left that I want to get through, so you're exposed to some things. Having had an automata class, there are a few things that I wanted to get in, even though we had to take the final exam a little bit early. And these things can help you with some sort of proofs. They can help you with thinking about certain types of problems. And it's good to be exposed to them, even though obviously in this case they're not going to be on the final because we've already done that. And you will see some of these things again, these concepts again, in the compiler class. So we're going to go and cover these things, these last couple topics. So today we're talking about pushdown automata. And let's actually talk about what the motivation is for those first. Let's go and get into this. All right, so pushdown automata, essentially we had context-free grammars. And those context-free grammars were used to define context-free languages, which included all regular languages. So if you remember, we had that Venn diagram of here are all the regular languages. Surrounding that is a larger class of languages called regular languages, and they're called context-free languages, which include all regular languages. So we had something more powerful than as a representative mechanism than we had with DFAs or NFAs or regular expressions. But the problem with those is that grammars aren't machines that can be used to either accept a string or reject a string given some language that it defines. And we looked at some parsing algorithms to do that, and parsers can help with that. But a parsing algorithm still really isn't a machine or a model of a machine. It's really just a computer program that does something with that code. And it's not the same thing as like a DFA where you have this well-defined formal machine that you feed in a string and it says yes or it says no. And we can use those machines to prove things and use those machines to put things into certain categories and so forth. So the idea here is it would be useful to have some sort of formalized machine, kind of like a DFA, that accepts languages that don't just include regular languages, but also include context-free languages. So today we're going to look at such a formal machine, and that's going to be what we're going to call a pushdown automata, or pushdown automaton if it's a singular. And we're going to shorten that throughout the lecture to just a PDA, which stands for pushdown automaton or automata, depending if it's singular or plural. All right, so getting into what pushdown automata is, it's going to look a lot like a DFA. In other words, it's a string accepting machine, just like a DFA or NFA. And formally, it's defined a lot like a DFA, but there are a couple key differences, as we'll see. The first thing is instead of a quintuple, it's a sextuple, meaning it has one extra part, this gamma thing tacked on the end. But you'll notice these parts are all the same things we had with a DFA. Q, sigma, delta, defined start state S, and a set of final states F. We've added this thing gamma on the end of that. So let's look at the individual pieces. So all of the parts are the same except for two, as a DFA, except for two. And the two things that are different are this gamma and the way the transition function works. So everything is the same except for those two things. So the first difference is that delta, which was the transition function with DFAs, is now a transition relation. And what it does is it maps elements of Q cross sigma union lambda cross that, and it says all elements. I should really fix that and take that out, and it shouldn't say all elements because it's not a total relation. It's just a relation, so it doesn't have to be all of them. And let me go back a page and take out that all out of there as well. And let's restart where we left off. Okay, so it's basically mapping elements of Q cross sigma union lambda. So in other words, it's all the symbols of the alphabet, plus we're allowed to have lambda like we had with an NFA. But now we've also crossed that with this gamma star. And to make sense of that, we need to look at what gamma is. So let's go down and look at gamma. So gamma is a finite set of what are called stack symbols, or also like what we're calling the stack alphabet. So we have two alphabets here. We have the input alphabet like we had before, and we've added onto it the stack alphabet, and symbols that we can put onto the stack or pull off of the stack. And so going back up here, we're mapping that to elements of Q cross stack alphabet star again. So in other words, what we're doing is we're mapping a state symbol stack string triple to a new state stack push string pair. And note that that transition relation has to be finite. So this is a finite state machine like the other ones were, just like a DFA, just like an NFA. It's still a finite machine. The only difference is we've added a stack, and in our relation, we also look at the stack to decide what to do and pop things off the stack, and then when we transition to the new state, we can push things back onto the stack. Now we're going to look at how these work in a little more detail in a second, but note that it's like a DFA that has a stack to store things on. But the stack alphabet has to be finite, and the transition relation has to be finite. So it's still a finite state machine. It's like a finite state machine with a stack. Okay, now before we get into how this works, let's talk about the concept of what's called a configuration. And a configuration is kind of like the state that the machine is in. And it's not good enough to just call it the state, because the state just says, well, that's what state in Q we're in. So a configuration is where we are as far as the state, where we are as far as what our input is, and where we are as far as what's on the stack. So a state is, you can think of it as the current state plus the input that's still left that hasn't been processed, plus whatever the stack looks like right now. So that can be thought of as the current state of the PDA, but we're going to use the word configuration instead of state because state implies one of the elements of Q, our set of states, where really we're talking about the configuration of how the machine is right now. What input is still left? What's the stack look like? What state of the machine are we actually in? And when we start the machine up, the configuration, the initial configuration or the starting configuration always looks like this. The start state, some string of input W, and nothing on the stack, or the empty stack. Okay, so the stack is going to be, when we write it down, it's going to look like this. So this is going to be the bottom of the stack here, with a bunch of symbols built up on it, and this is going to be the top of the stack. And remember, the stack alphabet has to be finite. So there's a finite number of different symbols we can put on there. So, but the bottom is going to be listed on the left, and the top is going to be what's at the end, or the last thing that's in that string. So when a new string of symbols is added to the stack, it's added to the top. Which means that since the top is on the kind of right-hand side there, that's where we add the new string of symbols, all the way at the end here. So when a string is popped from the stack, it's always removed from the top. It's always removed from this end. So in other words, you can't go into the middle and pull things out, or go to the bottom of the stack and pull things out. We always have to remove things from the top. Now we could pop things off and then replace it with other things. We could do that. But notice we're always going to be adding to the top and taking from the top. So in other words, the stack is a first in, last out configuration. So we're going to put things in, they're going to build up in the stack. When we pop things off, it's going to go take them from this end. So it's always going to be the right hand end that we're going to be manipulating in the stack. All right, now, oops. Okay, so transitions, members of the transition function are going to look like this. In other words, remember we had a triple mapped to a double. So in other words, this is a state, symbol, stack contents, triple, mapping to a new resulting state and new stack contents here. And this is the top of the stack. So in other words, this is saying that the transition from state Q1 to Q2 can happen if C is the input symbol, the next symbol, single symbol that's coming up on the input, and this string, gamma, this is lowercase gamma 1, is on the top of the stack. So if we see that on the stack, have that on our input, and we're in this state, then we can take this transition. And when that transition happens, that means we're going to pop this from the stack, push this onto the stack in place of it, and change our state of our current state to Q2. So in other words, if the pushdown automata is in state Q1 and C is the next input symbol, and that gamma 1 is on the top of the stack, then we remove gamma 1 from the top of the stack, push that gamma 2 onto the stack, and go to state Q2. And let me just fix a formatting problem here. Okay. All right, so moving on to those transitions, there's a couple things that are important to note here. So when we have this transition that looks like this, note that if gamma 1, if this is lambda, then that means lambda has to match the top of the stack. But lambda always matches the top of everything. There's always an empty string at the end of the stack, whether it has a explicit lambda or not. So that's basically saying that lambda is not indicating an empty stack in transitions. It's indicating that that transition can always happen without checking the stack. In other words, since that can match everywhere, we could say we could take this transition no matter what. Just like a lambda transition in an NFA, it can happen for no reason. So we could, as long as we have this symbol as our next input symbol, and we're in that state, we could take this, or not take it, with that lambda there, and we could transition to this. So in other words, it's not indicating an empty stack. It's indicating that we don't care about what's on the stack. We're going to pop lambda off of it. It's going to leave it as it was. So in other words, leave the stack alone, take the transition, but replace it with that. Now, sometimes, as we'll see later on, you can use special symbols to indicate the bottom of the empty stack. Sometimes $, sometimes the pound sign or hash symbol, as people now call it, or the \0 for a null. But we'll talk about that a little more later. But in other words, don't think that when you see a lambda here in a transition function, that means the stack has to be empty. That's saying take it, can be taken without checking the stack. Now, the way that the pushdown automaton works, it works like this, to accept strings. It basically says it accepts a string if and only if all the input symbols have been consumed. So in other words, our configuration gets to the point where there's no input left. The state that it was in when it stopped or when it ran out of input symbols was a final state as defined in F. And the stack has to be empty. In other words, all the symbols have to be off the stack. If all three of those things are conditions are met, then it accepts that string. If it runs out of input symbols and stops in a non-accepting state, even if the stack is empty, rejects the string. If it stops in a final state and there's still stuff on the stack, rejects that string. So the only way that it can accept a string is if all the input symbols have been consumed, it stops in a final state, just like a DFA or NFA, and the stack has all been, symbols on the stack have all been consumed. So a string is accepted if in other words, a string exists or is accepted if there exists some computation of that string, meaning a way of processing that string such that it can result in an accepting configuration that looks like this. Now, the converse of that is a string that gets rejected if it halts in a non-final state. It can't make a move. In other words, there's no entry in delta that matches the configuration that the machine is in. So kind of like an NFA, where if we get a state that cannot be, we can't move to another state, there's no defined transitions, it immediately rejects. Same thing is true here. Or if it stops and the stack is not empty when the machine halts. All right, so just like with DFAs and NFAs, to help us visualize pushdown automata, we can use a graph. But we have to change a few things. We have to change how the transition function works. So let's take a look at how we would make a PDA graph. So to make a PDA graph, the idea is they're going to work just like a DFA or NFA graph, where we have states are going to be circles. We're going to have transitions or arrows between those. But because the arrows also have to look at the stack to make the decision whether to take that arrow, we're going to have to label them a little bit differently. So in other words, the way we're going to label it differently is a transition that looks like this in the transition function, just like we saw earlier, is going to be drawn on the graph with an arrow from state Q1 to Q2. But we're going to label it with the character that's the input, what's on this has to be on the top of the stack, and what gets pushed on the stack in place of it, or in place of that when that transition is taken. So in other words, if C matches the input and gamma 1 matches the stack top, then the transition can be taken. And when we do that, we basically remove C from the input. We consume that input. We pop the gamma 1 off the stack. We push gamma 2 back onto the stack. And note that gamma 1 could be lambda. meaning we don't look at the stack and nothing gets pulled off of it, but this gets pushed in place of it. Or this could be lambda, meaning we pop this off or replace it with nothing. Those are allowed. But we always have to have the state we're going from, the state we're going to. And these could be the same state, just like with a DFA where it can loop back to that state. We could have that Q1 go to Q1. But these both have to be elements of Q, both have to be states, and C has to be an element of our sigma, our input alphabet. And these have to be strings of 0 or more symbols from the stack alphabet, capital gamma. Okay, a couple notes about those transitions. That, again, if C is lambda in a transition, the transition can be taken with no input being consumed, just like with an NFA. So this can be lambda or a single symbol from the alphabet. If Y1, if this is lambda, then the transition can happen without checking the stack or popping anything off of it. Another typo here. And then if Y2 is lambda, then that means when we pop this off and consume that symbol, we just don't push anything in place of it. So when that transition is taken, nothing gets pushed onto the stack. Now, I think to make this make more sense, looking at examples always ends up helping. So let's look at a few examples of pushdown automata defining certain languages. All right, so here's a pushdown automata for the language A to the N, B to the N, where N is greater than or equal to 0. Now, we have seen this language before, and this one we had proved previously several lectures ago that was non-regular. So we know we could not make a DFA or NFA or regular expression for that language, but we're going to make a pushdown automaton for it. So here's the pushdown automaton for that. Notice it only has 2 states, Q0, Q1. It only has 2 input symbols, A and B. That makes sense. And here's the transition function. We're going to look at that a little more carefully in a second. It starts in Q0. The final states are both 0 and 1. And that's because this is greater than or equal to 0. We have to handle the case where it's 0. And the stack alphabet is just the letter A. Now, to make this make sense why this is set up, let's take a look at the graph of that. So here's what the graph of that looks like. So we've got starting in Q0, both of them are final. We loop back to this from A on lambda, we push an A. So in other words here, anytime I see an A, I don't care what's on the stack, I just push an A on top of whatever was on the stack originally. Again, this does not mean the stack has to be empty. This means we don't care about what's on the stack. So in other words, I get an A, I shove an A on the stack. And then down here, as soon as I start getting a B, I say if I have a B and there's an A on the top of the stack, I pop the A off the stack and I push lambda. And I do the same thing here. So for every B, I get an A. So if I ever got another A when I was over here, I would immediately reject. So the idea here is pretty straightforward. The way that this works is basically for every A that we see when we're starting out, we push an A on the stack. So we're kind of shoving the A's that we get onto the stack. Now, one interesting thing, this doesn't have to be A. We could use any symbol down here. The stack alphabet doesn't have to match the letter that we're representing. It just makes it a little bit easier to think about. In other words, here we're saying, I could say every time I get an A, push a period onto the stack. And so we're using those tick marks to count up how many A's we had. And then once I start getting B's, I start pulling them back off the stack. And so since the machine will only accept if it stops in a final state and the stack is empty, then when this stops, for every B, since we've popped an A off of the stack, if it stops and the stack is empty, we know the number of B's we had matched the number of A's. And if we ever got another B or anything else in here while we were waiting, we would have immediately rejected. So notice looking at this machine, it makes sense. We see an A, push an A. We see a B, pop the A off the stack, pop all of them off until it's empty. If we stop and the stack is empty, we know we've matched a B for every A that was pushed. So we know the number is the same and we're in a final state, so we accept. All right, so that's the first example. So in other words, when the input is exhausted, if the stack is empty, then we know the number of B's match the number of A's. Otherwise, it rejects. So if there's stuff left on the stack, we had more A's than B's. if we got to a point where we got a B and there were no A's on the stack, we don't have a transition for that, so we immediately reject. So if there are more A's than B's, we reject. If there are more B's than A's, we reject. If there's any other symbol that shows up, we reject. Works and makes sense. All right, let's look at another example. Balanced parentheses. So this is all sets of balanced parentheses. In other words, not just nested inside each other directly, but open, close, or open, 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 close, close, open, close, that whole thing in parentheses, that whole thing in parentheses, that whole thing with parentheses after it. So pretty much all sets of balanced parentheses that are balanced correctly. So here's what the a PDA looks like for that. So the pushdown automaton for that, our input symbols are just open and close. We only really need one state, which is remarkable to think about because this seems like this is a more complicated language than the previous one. And you'll notice we really only have two transitions here. We have from Q0, when we see an open parenthesis on our input, and we don't care about what's on the stack. We push that open parenthesis onto the stack. When I see a closed parenthesis and I have an open parenthesis on the stack, then I just pop it. I just pull it off of there and say we're good. So in other words, every time I see an open, I'm going to push one on the stack. And for you, I guess that's this. And anytime I see a close, I'm going to pull that one off the stack and then move on to the next symbol because I've matched that close with the open that we already saw. All right, let's look at the graph of it. So here's the graph of it. I should have a start arrow here, I guess, pointing into that. But notice that we have open parenthesis. We don't care what's on the stack. We push the open parenthesis. Close parenthesis with an open parenthesis on the stack. Pop it off. Don't push anything in place of it. So what this is going to do is as I see opens, I'm going to push them onto the stack. As I see closes, I'm going to pull them back off. And if I get to the end of this input string that was passed into this, and I have nothing left on the stack, then I had no opens without closes. And notice if I did get another close where I didn't have something on the stack, it would immediately reject and say, well, there's an extra close. So this is very similar to the A's and B's one, but in this case, all the opens don't have to be together. All the closes don't have to be together because I'm allowed to take a close and stay in the same state and get more opens, push them, get more closes, pop them. So this is a way to make sure the opens and closes all match each other. So when a parenthesis is encountered, we push a open parenthesis onto the stack. When a close is encountered, we pop a close off the stack. And the idea there, again, if the input's exhausted and the stack is empty, then all open parentheses must have been matched with a close. So the machine accepts, otherwise it rejects. It's a very simple machine to do something that we could never do with a DFA. A DFA could not do this, but we can do it with one state and two transitions with a pushdown automaton. Okay, let's look at one more example here. So this is like the WWR or have a string in reverse, but I've stuck this letter C in between there. So in other words, we have a string of 0 or more A's and B's, and then we have a C in between those two strings. And then afterwards, these have to be match the reverse of those. In other words, if we had A, B, B, C, we have to have B, B, A. This W here has to match that one, but be the mirror image of it. In other words, we flip it around in reverse. Those two ends have to match each other with a C in between them. All right, so here's the pushdown automaton for that. Again, only two states needed. And so here's what the graph of that looks like. And looking at that graph as we have it there, you'll notice that we've got this kind of A. When I see an A, I push an A on the stack without caring about what's on the stack. When I see a B, I push a B on the stack without caring about that. So this is the part where we're pushing those A's and B's. And to make sure they match in reverse, we've pushed those A's and B's on there. When I see a C, I don't care what's on the stack. I don't push anything on. I just jump over to here to say now I'm at the point where I'm after the C. I'm now going to pull those off in reverse. So when I see an A and I have an A on the stack, that's the one that matched the last thing that I pushed on there. And since this is automatically reversed, since the stack is kind of in reverse order, so then I just pull all those off. And if I get to the end and there's nothing left on the stack, I know I've matched every symbol of W with one of these ones from WR, and so I accept that. Now, one quick thing that I want to point out here is that pushdown automata are non-deterministic in nature. Notice we have that lambda, we have the ability to have lambda transitions, we lambda as an input symbol. We have the ability to take that operation when we see lambda as the stack top. But that non-determinism in PDAs can make it hard to look at them and see what's going on. And it can also make them difficult to comprehend, because all that matters is there is some computation that gets you to that. Now, non-determinism comes from two parts of the way that pushdown automata work. The first one is that there's no way to encode transitions that should be taken only when the stack is empty. When we try to do that with a lambda, it doesn't care what's on the stack. The second problem comes from there's no way to encode transitions that should be taken only when the input is empty. In other words, only when input gets exhausted. So that creates a problem where we have non-determinism. So the solution to that is to add a special marker that means this is the end of the stack, or this means the end of the input. And a lot of DFAs, you'll see they do that. They set it up so that the idea is that we add this special symbol that cannot appear in the input and it cannot appear in the stack alphabet, but it means the end of the input or the bottom of the stack. And a lot of times you'll see a $ sign or a pound sign or a null symbol, null character, \0 used to represent that. And that can get rid of a lot of the non-determinism, make them a little bit easier to create for certain types of languages. All right, a couple final thoughts here. Every context-free language has a pushdown automaton that defines that same language. Thus, every context-free grammar has a corresponding pushdown automaton that acts as an acceptor for the language of that context-free grammar. So in other words, a pushdown automaton or pushdown automata are a class of machines that can act as acceptors or can define every language that we could make with a context-free grammar. And that's going to lead us back to that Chomsky hierarchy that we talked about before, except this version is a more complete version, that on the inside, the narrow ones here are these regular languages. And that was everything we could do with regular expressions, DFAs or NFAs, or linear grammars. Outside of that, we have these context-free languages, which are context-free grammars, and pushdown automata can represent context-free languages. It turns out that we have something outside of that too. We have context-sensitive languages, which are context-sensitive grammars. In other words, grammars where you can have context determine what happens next. In other words, you can have more than just a single variable on the left-hand side of a production. And notice there's also a thing called a linear bounded automaton that can handle those. We don't have time in this semester to cover these. You might, if you go on to grad school or have another automata class at some point, you might look at linear bounded automata. And then outside of that are what are called decidable languages, and then there's what are called semi-decidable languages, which are all things that Turing machines. And Turing machines are basically, we're going to look at that next class. We're going to look at Turing machines and how they work, but they're a computational model, kind of like a pushdown automata, but with a little more capability. But that Turing machines are kind of like a formal machine model that can do anything that's computable or anything you can do with a computer algorithm. Now the question is, are there things outside of that? Are there things that you cannot do with a computer algorithm? The answer is yes. There are things that are outside of that that are not computable. And one example of that is this thing called the halting problem, where writing a program that looks at other programs and decides whether they will eventually complete or not, is something that's outside of this computability. And we'll talk a little about that next class, but next class we're going to focus on Turing machines. But just notice that we can do a whole lot of things with this. Any programming language you've used, a compiler if you've used, those have to be or are generally inside of this context-free languages area here. There are context-sensitive programming languages in some case, so they use stuff that's outside of that out here, this context-sensitive area. But notice that any program you've ever written, any program you ever could write, is going to be inside of this Turing machine bubble of this. And you cannot get out of that. If you have a problem that is not in that what Turing machines can do, you can't write a computer program to solve it. The problem is kind of untouchable by computer programs at that point. Okay, so that's it for today. The last thing, let me fix this. All right, so the last thing, we have one lecture left, and then we're going to cover Turing machines, at least give a brief introduction to them. I wish we had a few more weeks in the semester, and we could spend some time proving that context-free languages can be all kind of represented by pushdown automata using another pumping lemma, the pumping lemma for context-free languages. And we could also spend some time proving some things with Turing machines, but unfortunately we've only got one class left. So I really wish we had more time this semester, a few more weeks, and we could have some labs and some stuff playing with these and make a program that simulates Turing machines and pushdown automata and watch them run and do things. But what I would encourage you to do is focus on that bonus lab. Also keep in mind there are still bonus points available for the final exam with the black box automata. I'm kind of disappointed we didn't get more time for you guys to ask questions about that, because that's a fun problem to try to figure out. And the one that I gave for this semester is not overly difficult to figure out. If you email me some more test strings, I'll get back to you with whether they pass or fail. But if you want some bonus points, do that. Also, if you want bonus points, do the bonus lab, because that's actually a fun lab to do too. All right, that's it. Stay safe. With one class left, and then you're free from me, maybe forever. But I was pretty happy with how you guys performed on the final exam, so good job there. Do watch the last couple lectures, because these things can be helpful for your future career. And it's just fun stuff to know anyway, if you're interested in computers and how they work. All right, that's it. And I'll see you guys for next lecture. And then after that, have a good Christmas break. Maybe I'll see you guys around in the spring.